Hi everyone and welcome again. In this lecture I want to go over the application of determinants and the Cramer's rule. So let's start. First thing you need to know is what is the joint of a matrix. Now recall here, if I put C the matrix of the cofactors, so it can be written like that. So if you have an n by n matrix, then you can calculate C11, put it here, C12 up to C1n and so on. Now, what is that? So again, we write that as a matrix of the cofactors. So if a cofactor was Cij is -1 to the power of I plus j times m, which is the minor of ij. So what you can do is calculate the matrix of the cofactors. And then if you take the transpose of C, which is the matrix of the cofactors, then you can call that the adjoint of A, which is given by the expanded form is like that, C11, C21. Again, this matrix is the transpose of that matrix. So this is the transpose of that matrix, and that's called the adjoint of A. Now let's see how this is used. An example, we show this very nicely. So if we have a matrix, say I took a 3 by 3 matrix here, and you can calculate all the four cofactors. I did for the first one, C11, if you calculate that is -1 to the power of 1 plus 1, which is 2, and times the minor of A11, which is that the determinant of that matrix, and I wrote it here, and you get 4. I didn't do the rest because it's pretty straightforward. So if you calculate all of them, then you get the matrix of the cofactors C, which is this matrix 1, 4, 2, 6, 0, 3, 7, 1, 2. Please try to find them one by one so you can remember and understand that better. Now, if I take the transpose of this matrix, I get the adjoint of A, which is 4, 6, 7. Again, all I did, I switched the rows and the columns. 1, 0, 1, and 2, 3, 2. Now, if we take A, our original matrix, and we multiply that by adjoint of A, so this is the original matrix we had, A from here, and we multiply that by adjoint of A, and if you do that multiplication, again, you can take the first row times the first column, which I wrote it here. However, and I put the entries here, that's A11 times C11, A12 times C12, and A13 times C13. So if you do that, I want you to notice something. This is 1, 1, this is 1, 2, and that's 1, 3, 1, 3. This one, it's 1, 1, 2, 1. They're not the same. 1, 2, 2, 2, 1, 3, 2, 3. And for this one, again, 1, 1, 3, 1, 1, 2, 3, 2. These are not the same. So, and if you do that, you're going to see it's going to be the same for here, and for here. But basically, if you find those numbers, and I have it here, if they're the same, then you get a scalar. So that goes for diagonal entries. And the rest, if those subscripts are not the same, you get zeros. But what is that number is just the determinant of A. If you calculate the determinant of A, you are going to get 3. So now what can we do here? If I have this, I can take the determinant 3 out, factor out 3 from here, and you are going to be left with the identity matrix. So basically, let's recap that. A times adjoint of A is the same thing as the determinant of A times I. if I isolate I, a joint of A divided by the determinant of A, or divide both sides by the determinant of A, and you get I. But it's interesting because a matrix times A, if you get I, that means it's the inverse of A. So inverse of A can be written as a joint of A over the determinant of A. Or you can say, I wrote it here again, inverse of A is a joint of A over the determinant of A, or 1 over the determinant of A times a joint of A. That's another way of finding the inverse of A. For a 2 by 2 matrix, we had the formula, so please try that for a 2 by 2 matrix. If you have A, B, C, D, go over the formula, and that's the formula used to find the inverse of A fast. It's 1 over the determinant of A times, and find the adjoint of A, you'll see. Next, let's go over the Cramer's rule. That's a rule to solve systems of equations. So if you have a system of equation A times X equals to B, again, I put those arrows. This can be vector matrices. Now A is an n by n matrix. It has to be n by n. X is n by 1, and B is n by 1 also. You can solve for x1 doing the determinant of A1 divided by the determinant of A. The determinant of A is the matrix of the coefficients. Same thing for x2 and same thing for xn. So you can use the formula, use the determinants, and get the values of the variables. Now where ith column of AI, ith column is B. So you just take, if you want to solve for x1, you take the first column of A and you change that by the matrix B, or the column matrix B. Let's go over a little example so you understand how this works. For a 2 by 2, a simple system, x1 plus 2x2 equals to 5, negative x1 plus x2 equals to 1. I did solve this by using elimination, so I added the first 6, x2 equals to 2, then you can substitute and find x1. x1 is 1. So the solution is 1 and 2. Let's see how this works, but it works by using the Cramer's rule. First of all, the matrix of the coefficients, and it's 1, 2, negative 1, and 1. You can find the determinant of that matrix, which is 3. Then if you want to solve for 1, and you substitute that by this column. So the constant column is phi 1. And if you substitute that here, you can find the determinant of the numerator, which is 3 divided by the determinant of A. 3 is going to give you 1. To solve for x2, you take the second column and you substitute that by the constant column, and it's 1, 5, negative 1, 1. And if you take you find the determinant of that, you get 6 divided by 3, and that answer is true. And as we see, the solution is 1, 2, which is the same answer. There's some other little applications of determinants. Let me just introduce you to that. If you want to find the area of a triangle in the xy plane, then you can just find this determinant, and that's going to give you the area of the triangle. So it's if again the vertices, they have to be at x1, y1, x2, y2, and x3, y3. Let's look at the determinant is negative 1/2, plus or minus 1/2. x1, y1, 1, x2, y2, 1, and x3, y3, 1. I did a little example here for you to see. So if we have those points, those vertices, and so this should be y3. So I put it at 0, 0, 3, 0, and 3, 4. the area of this triangle, if you use the formula, is 1/2 base times height, so it's going to be 1/2 times 3 times 4, and that's going to give you 6. Now let's use the formula. It's negative 1/2. So again, x1, y1 are 0, 0, x2, y2 are 3, 0, and x3, y3 are 3, 4. I expanded this along the first row because it was faster. We have a couple of zeros, so it's negative plus or minus negative 1/2 negative 1 to the power of 1 plus 3. It's right here, and times that the determinant, the minor, which is 3, 0, the determinant of 3, 0, 3, 4. And if you do that, you get plus or minus 6. And of course, area is always positive. That's why the formula says plus or minus. You have to take the positive one. Another application is test for collinear points on xy plane collinear. That means if you want to know if 3 points they are on the same line, you can just use this determinant. Put the coordinates of those points, and if you find the determinant and the determinant is 0, then you can say those 3 points are on the same line, or they are collinear. From the second one, you can find the equation of a line in xy plane. So an equation of the line passing through the points x1, y1 can be given by this formula. These are the variables x, y, and then you just substitute x1, y1. Here it's 1, x2, y2, and that's 1. And you solve it, put it equal, find that determinant with respect to x and y, and solve, put it equal to 0, or you can solve for y. That's going to give you the slope-intercept formula. So it's pretty easy. Please do the examples in the book and you'll see. And I think that's it for this lecture. So know the Cramer's rule and those little applications, which is going to be very helpful in the future. Thank you for watching, and I'll see you in my next video.